class, this is Dr. McGonigal with another Research Methods 2 lecture for you. Today we are going to talk about calculating correlations using SPSS. In this video, you'll learn how to conduct and interpret tests of correlation using SPSS and learn how to create and read a correlation matrix. As a reminder, make sure you're caught up on your Price readings, especially Chapter 13. In terms of where we are with our stages of data analysis, we are still in inferential statistics where we learn how to test our hypotheses. So in our last video lecture, you learned about null hypothesis significance testing and which statistics go with which types of data and variables. So if you haven't already watched that video, please stop this video and watch that one before you continue on. In our last video, we went over the guidelines of how to choose which statistical test to use. We're not going to cover them again today, but I wanted to include this to point out where we are in terms of our statistical tests that we're focusing on today. So if you have two quantitative variables, both your predictor and your outcome are quantitative, then you can use a correlation test, and that's what we're covering. When do you use correlational tests? Well, there is a broader term called correlational designs, and those include both correlation and regression analyses. We use these when the focus of our study is on the relationship between two or more variables. We use correlational designs when we have a continuous or Likert type dependent or outcome variable and a continuous or Likert type predictor or independent variable. These are our quantitative variables that we've been talking about throughout the semester. Correlations tell us the degree of linear relationship between variables. So it tells you strength of that relationship and the direction of that relationship, whether it's positive or negative. The statistical significance of a correlation tells us whether the correlation value is statistically significantly different from zero. So remember last time how we talked about how zero is the lowest possible correlation. If your correlation is not zero, we need to know, is it large enough to be statistically significant? Can we be confident that it's not zero? That's what our statistical significance tells us. Again, we use p of less than 0.05 in most cases to determine statistical significance. But in some cases, you may want to use a lower p-value, like we talked about in our last video. For your projects, you will want to make sure that you're using your composite scores when computing correlations. Do you remember what composite scores are? We covered this in your data cleaning module, so if you are confused about that or if you forget how to create your composite scores, make sure that you go back to the data cleaning module to learn how to do that. Our composite scores are our average of multiple items that are within the same scale. We combine them to create one average or mean score for an individual to represent their standing on a particular construct. We went over this last time, but just as a reminder, your strength of the correlation ranges from -1 to +1. The weakest is 0, and the strongest is -1 and +1. Don't fall into the trap of thinking that a negative correlation is a weak correlation. A correlation of -1 or -0.9 or even -0.8 is a very strong correlation. It's just that the direction of it is negative. A negative correlation indicates that as one variable increases, the other variable decreases, whereas a positive correlation indicates that they both either increase together or decrease together. Here's an example of a correlation. This is called a scatter plot, so you can see that each dot represents someone standing on a variable x along with their standing on a variable y. This represents a very strong and positive correlation. We can tell that it is a strong correlation because the dots are all clustered fairly close together around that line. And we can also tell that it's positive because as scores on variable x increase or go up or go farther away from this point here and go further to the right, Scores on Y also go higher up, further away from the low and closer to the high. This is also a very strong correlation. Again, you can see that the dots on the scatter plot are clustered fairly close together and close to the line. However, it is a negative correlation, and we know that because as scores on variable X increase or go from low to high, scores on variable Y decrease. They go from high to low. These are examples of more moderate correlations. They would still probably be statistically significant, but they are not as strong as the previous examples because they're clustered further from the line. To run a correlation in SPSS, it's fairly simple. First of all, you want to make sure that you have your composite variables created and that you've done any reverse coding that you need to do on your items before you're creating those composites. Then you go into Analyze. Once you have your composite variable and you're ready to calculate your correlation, you click Analyze, you scroll down to Correlate, and you choose Bivariate. When you do that, a screen will pop up that looks like this. It says Bivariate Correlations, and you can move the variables of interest from the left-hand side over to the right-hand side. In this case, we are correlating self-efficacy with a time to test score. So we have those two variables in our variable list. The next step is we can either paste our syntax into a syntax file and run it, or we can click OK. This is the output for our correlation test in SPSS. What you see here is a correlation matrix. You have your variables on the left-hand side here, and you also have them in columns as well. So you can see that our first variable here is self-efficacy. This is our Pearson correlation, that's what we're looking for. The correlation of self-efficacy with itself, self-efficacy, is 1. So anything correlated with itself has a value of 1. Self-efficacy is correlated with test score at time 2 at 0.86. 0.86. Now, that is actually a very strong and positive correlation, right? So that means that as self-efficacy increases, people's test scores at time 2 also increase. Is it statistically significant? Well, we can tell that by looking at the next line down. We see this thing here that says sig two-tailed. That's our statistical significance. In this case, the p-value is 0.001. This is less than a p of 0.05, less than our cutoff value of 0.05. So we know that our correlation between self-efficacy and test score at time 2 is statistically significant. The third line here is the N, and that's the number of people that are included in your analysis. You'll note that the information that is above and below what we call the diagonal is the same. So why is that? Well, if we look here, self-efficacy is correlated with test score at time 2 at 0.86. If we go down to test score at time 2, and it's the same thing, correlated with self-efficacy, it's also 0.86. So anything below what we call the diagonal, this line here, will reflect what's above the diagonal. Here's an example of how you would report your correlation in a paper. The results show a significant positive relationship between self-efficacy and test score at time 2, comma, lowercase r italicized equals 0.86, comma, p italicized equals 0.001. You want to provide an exact p-value in your paper because that's what APA style dictates. Then you would say this indicates that higher levels of self-efficacy are related to higher scores on the test at time 2. Now you can also compute correlations with multiple variables at the same time. How do you do that? Well, it's very similar to what we just went over. You click on Analyze, you go to Correlate, you click Bivariate. On the next screen that pops up, you can add as many variables as you want to move them over from the left-hand side to the right-hand side. Remember that you only want to use quantitative variables when you're running these correlations. After you have all of the variables over that you want to include in your correlation test, you click Paste to paste your syntax, and then you click Run in your syntax file, or you just click OK to get output. Let's take a look at the output from these multiple correlations that we're running at the same time. In this case, we have 3 variables. We have self-efficacy, we have score on test, which is their test score at time 1, and we have our time 2 test score. So we've got self-efficacy, time 1 test score, and time 2 test score. And similarly here, we can see self-efficacy, our time 1 test score, and our time 2 test score. We can see our 0.86, which we attained last time when we ran just self-efficacy as correlated with test score at time 2. But we also have some additional ones, including self-efficacy with our test score at time 1, which is 0.297, and is not statistically significant. We also have test score at time 1 correlated with test score at time 2, and that correlation is 0.981. It's very strong, it's almost the same. So people tended to perform similarly on their tests at time 1 and time 2. This is the diagonal that I was talking about before. Anything correlated with itself is a value of 1. So that's our diagonal, because self-efficacy is correlated with self-efficacy here, score on test is correlated with score on test here, and test score at time 2 is correlated with test score at time 2 here. And you can see that what is above the diagonal is mirrored also below the diagonal. It's the same results. Okay, so that finishes our discussion of testing correlations in SPSS. To wrap up, now you should know how to conduct a correlation test in SPSS and interpret and write up your results, and to create and interpret a correlation matrix.